Bem-vindos, bienvenidos. Welcome to Ask Tom Office Hours for Latin America and Iberia. I am your host, Chris Pedregal. A reminder, you can ask your questions in English, preguntas en portugués, preguntas en español. Michael Nowak is our expert today. O convidado de hoy es Michael Nowak, nuestro experto, Michael Nowak.
My name is Michael Nowak. I work in the MAA team, or Maximum Availability Architecture team inside of development. And I'm happy to be with you today for this office hours. We have the safe harbor statement always in our presentations. I probably will give you some things throughout this presentation that are forward-looking. What I did here for this slide deck was I tried to pick out some of my favorite slides from different categories of presentations I've done fairly recently. And they all fall into like these three main categories. So I want to talk a little bit about MAA Exadata and the history of the product and the platform. So we'll spend a little bit of time on that. I have a second section called Use Cases with Depth. So I picked some of my favorite technical slides, and I'm going to explain them in a little bit more detail, maybe than you've seen them. If you ever saw any of these slides online, or if you went to Oracle World, maybe you saw a presentation at some point in time. I'll try and give a little bit more depth to these things, and I have some stories that are kind of interesting that I can share. And I also have one slide at the end on kind of where we're going, and this is kind of where Oracle is going as a company, where Exadata MAA are going. And just to level set, I'm in the MAA team. This is not a purely MAA presentation. This is Exadata MAA. So you're going to see MAA and Exadata interleave through the presentation. So hopefully we'll have fun with this. It'll be light. I'll tell some stories, but it'll also be technical and interesting for you. I think it's really important just to reflect for a moment on the fact that we don't work on HA for the fun of it. Well, I kind of do because I love what I do, but there's obviously a tangible cost associated with downtime. And this slide kind of provides some compelling numbers about how expensive downtime is. And when we look at downtime, we're not just talking about unplanned outages, but we're talking about planned maintenance. We're talking about anything that interrupts your service level. So if you look at some of these numbers, they're quite staggering how expensive it is to have critical systems be down. So one interesting tidbit about this slide is that the example, the last example on the slide, the Amazon example, came out the day I was presenting at Oracle World 2018 on how important HA is and some of our Exadata MAA best practices. So it literally came out the exact same day, which I thought was ironic. And this slide covers what is MAA. So MAA in its most simplest terms, probably I've heard you're all very technical, so maybe you already know what MAA is, but in its most simplest terms, it's an HA blueprint. It's a set of configuration and operational best practices for you as customers. And it solves real world availability problems. It solves problems associated with unplanned outages, planned maintenance, and lifecycle operations for your systems. So another very important aspect of MAA is that it's been critical to the success of engineered systems. So engineered systems, about 10 years old. We bake all of our MAA best practices and high availability features into the engineered system. So that's been really important. And one interesting tidbit about MAA, it was really invented by Juan Loaiza, who's our EVP in the development group. Probably many of you may know Juan. If you've seen him, you can see videos of him online, and he's presented at the conference, and he's a great speaker. Anytime you get to see Juan speak, you should have a look. And he really invented MAA a long time ago, before even I was on the team. I've been on this team about 15 years. The team was formed earlier than that. So, and in the old days, what we would do is we would create white papers for customers. So we would go into our MAA labs, and we would work on a particular availability problem. And we would solve that problem. We'd document how to solve that problem, document what you as customers could do to solve that problem. We would give you a white paper that you could follow, and then you would have higher availability. And as you'll see through this presentation, in these days, it's evolved, and we're building more of this into the product, okay? So that's kind of what MAA is in general. And as I said, this isn't an MAA presentation per se. I could spend probably 3 hours talking to you about all the different MAA features that we have and best practices. But one very important thing to know about MAA is these tiers. So a long time ago, we had MAA, when it first came out, it was all about just having all the greatest HA features and best practices. And this is how you could, the systems with the highest, most stringent levels of availability, this is how you could achieve that level of availability. And several years ago, it was broken up into these tiers. And the idea is MAA is not just for systems that need the highest level of availability. MAA is really for every system. So every system has its own service level, and there is an MAA solution for every service level. So you just need to figure out where you fit and which one of these tiers you fit into. And if you look at the tiers, as you proceed through each tier, you're getting higher and higher levels of availability. So for example, if you go from bronze to silver, you're adding redundancy at an Oracle instance level, right? With something like real application clusters. When you go from silver to gold, you're adding redundancy at an Oracle database level. You're adding another copy of the database through something like a standby database. And then when you go up to a highest level of platinum, we have things like Golden Gate. We have things like application continuity. And the key takeaway here is any system fits into one of these tiers. MAA is for everyone. It's very, very inclusive. And then when we talk about Exadata, you've probably seen this slide before, but the main point I want to make on HA is Exadata from day one has been built up with availability in mind. So high availability has always been very important to Oracle. It was the same way with Exadata. I've actually been on the Exadata team since the very beginnings, since the development of the product. And the key thing is the three primary tiers that we have in Exadata, the database tier, the storage tier, and the network tier, all have redundant components and a highly available software firmware stack tightly integrated. So that's the main thing I want you to take away here. Is we just came up on the 10-year birthday for Exadata. It was launched in 2008. We celebrated our 10-year, but we had a little party. And of course, MAA has been, MAA and Exadata have been tightly together the entire time. And there's a link here, because I can't talk, we only have a short amount of time today. There's a link here that provides a lot of other information around high availability on Exadata with MAA. Okay, so if afterwards you want to pick up some things that I wasn't able to cover in more detail, you can have that. Many of you, hopefully, are Exadata customers. You know what Exachk is. It's our best practice variance checker. So I was going to tell a little story about Exachk. Exachk's a very popular tool now, extensively used internally and externally by customers. It basically it allows us to do a very dynamic, real check of the system to make sure it's compliant with our MAA best practices. And Exachk was actually born from being just a wiki. So in the very, very early days, we wrote down all the things that we needed to be successful and highly available on Exadata in a wiki. And we wrote down what the problems were, what the check should be, and blah, blah. And then we tried to figure out how we could make this a tool. And there were some decisions whether we would go one way or another. Anyways, that was a very, very long time ago. And I thought it would be interesting for you to know that it used to be just a simple wiki with simple shell scripts a long time ago. So the other thing that's interesting is I run a meeting every Wednesday. This is a development meeting every Wednesday. And the best practices that you get, the MAA best practices you get from Exachk come directly from that meeting. So they are high quality because there's a lot of other development representation in that meeting, and we make sure that we get it right when we deliver it to you. Okay, so that's where Exachk best practices are sourced from. Okay, so X7, we have something called a do not service LED. And what it is you can see a picture of it here. It's on the Exadata cell, X7 or higher, this little white light right here, do not service. And the reason we have this light is this allows us to ensure that a data center tech will not shut down a storage server if the redundancy in the disk group is compromised. So this is a very good example of how we've integrated software and hardware together to achieve higher availability. So one of the things that could have happened in the past is data center tech may not be so savvy and be able to check all the software and make sure that them working on this particular cell is going to cause another problem. So we provide a very easy visual, do not service LED, to make sure that that doesn't happen. So the interesting part about this, and here's where the depth comes in. So how does this thing work? Let me step back for a second and explain to you how partnering works in ASM, because that's integral to how this do not service LED is lit up. So in ASM, and therefore on Exadata, we have the concept of failure group partnering. So failure group in Exadata is a cell, okay? And we have a concept of disk partners. So every cell in an Exadata rack will be partnered with 4 other cells, if there's 4 others that exist. And every disk within a cell will be partnered with 2 disks on each one of those 4 cells. So you actually have 8 disk partners on 4 cell partners, okay? So when you think about this do not service LED, what this really means is one of my partners has a problem with it. So if this cell is lighting up as do not service LED, it means one of his other partner disks has some problem. Maybe the disk failed, maybe there's a rebalance running, maybe a flash failed, something like that. So let me ask you a question that I will answer so that I don't have to put any pressure on you. If you were standing in front of a full Exadata rack and you saw cell, let's say cell 8, which is the one right above the database nodes, had this light lit up, what would that mean? What that would mean is that one of the partners, which by default is going to be either cell 9 or 10 or 7 or 6, has some type of issue on it. There's some type of failure that hasn't been completely repaired yet. Okay, so we light that thing up and we make sure that we don't take that server down. So another thing you may be wondering is, what about if I have normal redundancy or high redundancy? If I have high redundancy and I have a disk down and then I shut down a server, that's still only 2 copies that I've taken down, right? I still have a 3rd copy. That's true, but we still always light up the do not service LED, okay? Even with high redundancy, because we know that you don't want to have 2 of your 3 copies of data compromised. So that's a little bit more color, a little bit more depth into this feature. The basic reason that this feature exists is to prevent accidents, okay? There's another new component in the X7 called an M.2 drive. And before I tell you about the M.2 drive, I'm going to take you back in history and look at the way we used to do things on Exadata. So in the early days of Exadata, actually not really early days, all the way up through X6, we had a USB drive, and we would put the operating system and the cell software on the first 2 disks, all right? So we have 12 disks in every Exadata cell, and we would put the operating system and the cell software on the first 2 system disks. And that's the way we did it for a very long time. The cell USB was a boot arbitrator, basically, and provided some rescue functionality. And the operating system living on the first 2 disks, obviously we had 2 copies of the operating system and the cell software. And what that allowed us to do, to make things align, we would create a DBFS underbar DG disk group on disks 3 through 12, okay? So that was the old days, and that's how everything worked up through X6. Well, what we have in X7 is we have 2 M.2 drives in the system, and they take the place of everything that they serve the functions that I just described, previously done by the USB drive and the system disk. So basically what it means is these M.2 drives have your operating system, they have your cell software, they have your rescue functionality, and we have 2 of them for redundancy, okay? And so what that means is we don't need the USB drive, and we don't need the DBFS DG. So actually when you see an X7 deployed these days, or any future generations of Exadata, you're not going to see a DBFS DG disk group anymore. And so the main point of this slide, I'm telling you all this history because I'm trying to give you some more information on some of these things. But the main point of this slide is that you can pull these M.2 drives out when they fail without turning the server off. So we have hot swappable M.2 drives on the X7 server. And we test this, by the way. We go into our MAA labs usually quarterly and test some of this stuff. So we've actually done these things and made sure that they work. Another thing that's interesting is the flash drives are also hot swappable on X7 and higher. So you basically can take the chassis off, and as long as there's no power to the flash drive, which it wouldn't be if it had died, you can pull it out. So this slide kind of shows all of our I/O cancellation features, but the main new feature that's was illustrated when I first presented this at Oracle World this past year was database tier I/O cancel, but you'll get to see all of them. So check out this system. So we have a database tier and a storage tier. So this is a typical quarter rack, right? We got 2 database nodes and 3 storage servers. And the IOs are flowing and pumping between the system. Exadata is doing its thing, okay? What happens if we hit a slow IO in the storage tier on one of the cells? Well, we have something called cell IO latency capping. On the storage tier, we monitor the IO timings. And if one is taking too long, we will cancel it. If it's a read, we'll read from the mirror. If it's a write, we'll write to an alternate healthy location and deal with it later. So we know how to deal with slow IOs, okay? What if it's a hung IO? Hung IO can be really bad. If you have a truly hung IO that escalates all the way up to like a controller level problem, you can stall your entire system with this hung IO. So we have something called IO hang detection and repair. And we may even reset a whole cell if the problem is that bad to make sure that your system doesn't stall. Okay, so that's how we deal with a hung IO. What happens if you have a sick disk? What if a disk is about to die, its IO timings, its service timings are really bad? Unfortunately, this is just the fact of life, right? Well, we have a couple of things for that. We have predictive failure in the controllers, which has the controllers themselves have heuristics as to when the disk is going to fail, and it'll put it in a predictive fail mode, and we deal with that. And we also have something even on top of that called disk confinement, and that's an Exadata feature where we monitor the service metrics of disks and make sure disks and flash and make sure that things are being serviced the same across all the different components. If they aren't, then we potentially take one offline if it looks like it's sick. So you can see on the storage tier, we're able to handle a lot of different problems, right? What happens if we have an undiscovered hardware or software issue on the storage tier? That's a tough problem. Maybe we have a new bug, or maybe we have a network glitch on the InfiniBand network getting to the cells or something like that. We have a new feature to deal with that called database tier IO latency capping. And what this does is from the database tier, it monitors how long IOs are taking. And if they're taking too long, it will cancel them and redirect, okay? So that's all the features we have around IO cancel. This type of stuff is really hard to do, but when you talk about maintaining service levels, you need to do these types of things because these problems exist in real life. So in Exadata 18.1, we introduced something new called OLTP caching, smart OLTP caching. And it's best understood through the example that I have here. So we have a buffer cache on the top, and we have 3 storage servers on the bottom. 2 of them we're looking at the inside of them, and 1 of them we're looking at the front of it. Okay, so what happens in a normal Oracle system when database writer cleans up the buffer cache and evicts a buffer? Okay, so it needs to make space in the buffer cache. This buffer has to go. What we're going to do on Exadata is the primary copy of that buffer when it's evicted, of that block, is put in the DRAM cache on the primary cell. So if you notice, it's it's on the memory card in that cell. So that's the primary copy. The secondary copy, oh, by the way, I should tell you, this is a high redundancy disk group, so we have 3 copies of everything. The secondary copy is put on the low latency flash card of the secondary cell. And then the tertiary copy is put on the hard disk. So you see we have a tiered approach here. Why do we do this? Well, ASM typically reads the primary mirror, okay? Unless it's not available, then it'll go to the secondary. So you're gonna keep that in mind because you're gonna wanna know it for the next slide, okay? Let's look at this same system under the context of a failure, okay? So, yes, so let's look at this. So what we have is we have a SaaS application that's reading the primary mirror. So as I said, ASM will always read the primary mirror if it's available. So we have this application reading the primary mirror. Let's say we have a flash failure or a disk failure on the storage cell. So the primary copy of the data is no longer available. That's no problem, right? So we know remember we put the secondary copy in the flash cache of the second cell. So we get a low latency IO from the second copy. This is where the money is. This is where the trick is, okay? If you don't do this, if you don't do what we have here, you end up going to a hard disk and it's very slow, much, much slower than your system has gotten used to, okay? So reading it from the flash, you get a low latency IO and your service level is maintained. Now, we keep that third copy obviously still on the hard disk of the third cell for a rainy day scenario, right? It might be that if there's some problem with the second copy, at least we have the third copy. And in that case, we don't care if it takes longer to read that third copy, okay? And one of the really cool thing we do is after the initial storage failure is repaired, let's say it was a flash failure and the flash is replaced, we're not going to start reading that primary copy right away. We're going to monitor the cache warm-up on the system and make sure that it's adequately warmed up before we go back and start reading it again. Okay, so, and that makes sure that we don't, obviously when we first initially replace a flash, it doesn't have, none of the data has been populated. We don't want to start reading from it right away. So there's a lot of intelligence built into this. And this is how you can see like your service levels get maintained through some of these various failure cases. I'm going to talk now about something called Smart Rebalance. So this is a new feature, not available yet, but imminent. This is Smart Rebalance for high redundancy disk groups only, okay? It's going to be with GI19C. So many of you, if your DBAs out there, you've probably dealt with at some point in time running out of space in your disk group. In particular, you may have dealt with a problem where you had a failure and you ran out of space in your disk group while the rebalance was running, okay? The error message for this is the dreaded ORION 15041, okay? So that's the problem that we have on this slide. So in 18C and lower, we have a solution for this problem. And you will find this if you run Exachk that I mentioned before. It's in best practice notes. What you need to do is you need to reserve a certain amount of free space in your disk group to be able to complete a rebalance if you have a failure, okay? If you have less than 5 Exadata cells, you need to keep 15% free. If you have more than 5 or more Exadata cells, you need to keep 9% free, okay? And if you do this, you won't run out of space when you have a disk failure. Now, remember I was explaining before all the partnerships and things. You may start to make a connection with the previous slide that I was discussing. The reason, notice that the less than 5 Exadata cells, if you have less than 5, you have 4. That means each cell cannot partner with 4 other cells because you don't have enough cells to make that happen. I'm not going to get into the mathematics of why this is, but I will tell you that that partnering is part of the reason that we have a little bit more of a need for the free space on the first case, right? And when you have enough cells to partner with 4 other Exadata cells, as is in the 9% case, you don't have that problem anymore, okay? As it says here, you can run Exachk. It'll check the free space in your disk group, and it'll tell you, whether or not you have enough free space depending on your configuration. Now, this is today. What's tomorrow? In 19C, we have, excuse me, we have high redundancy, for high redundancy disk groups, we have something called Smart Rebalance. What we're going to do is we're going to say, if you don't have enough space to complete a rebalance after a failure, we're not even going to run the rebalance. We're just going to keep the disk offline. The third copy of the data is going to stay offline until the disk is replaced. When the disk is replaced, we'll resync the data using an ASM resync, okay? What is the benefit of this for you? For you, the benefit is you can fill up your disk group completely if you're using high redundancy. You don't need to save any free space at all. You can just fill it all the way up. And this has been a common complaint over the years for customers. They get frustrated with high redundancy because you end up, having to have 3 copies of the data, and then on top of that, you got to have all this free space. So this solves that problem. So you have 0% free with high redundancy disk groups. And I'm not sure how you fill up your cars with gas. In New Jersey, we can't fill up our own cars with gas. And so we go to the gas station and say, fill her up. So that's what you can do with your disk groups. You can fill her up. This feature is one of our long-standing kind of key HA features that we've had on Exadata that's a real differentiator. It's something called fast node death detection. And the simplest way for me to explain it to you is when a node dies in a cluster, sometimes it's hard to know that that node has died. So on a non-Exadata environment, you have to go through something called a CSS miscount. And that can cause a stall in your system for the length of the CSS miscount, okay? On Exadata, we do a neat trick where we call into the InfiniBand subnet manager and say, are all of the ports on this node that I think is dead offline? And if the InfiniBand subnet manager says yes, then we can safely assume that the node is indeed gone from the fabric. It turns out that the InfiniBand subnet manager has very real-time information about node ports, right? So this is a patented feature, and we've had it for a long time. The interesting thing is we had this on the cells before we even had it on the database nodes, but these days it's on both. Excuse me. So the net of it is you see a much longer blackout on non-Exadata systems after a node death than you see on Exadata systems. Let me ask you a question that I'll try to answer, which is, what is a disaster? So in terms of a system, what is a disaster? When should I fail over? So I don't think, one of the things we now don't want to just think in terms of Mother Nature here when it comes to leveraging our standby systems. So obviously, when we talk about disasters in systems terms, we need another copy of the database. And typically that's a standby database. So we need to be able to fail over to a standby database. I'm sure you know we have things like Active Data Guard these days that allows you to have a standby database that you can open read only and do work against it. You can run backups again. You can do standby first patching against it. But in terms of dealing with disasters, don't think just in terms of Mother Nature. Think in terms of what will cause my database to be down so long that my service level will be impacted. And whatever those events are, and in those times you want to be able to use your standby system. So let me give you an example. Let's say you choose normal redundancy and you have some type of double failure, whether it's you have one piece of storage that's offline and then another cell goes down or something like that. If you have a disk group get dismounted, that's a disaster. You want to be able to fail over to the standby system in that case. And you want to feel comfortable failing over to the standby system. Corruptions. We do a lot inside of our code to deal with corruptions and auto repair them. And we have all these special features in the standby where we will auto repair corruptions. But if there are certain types of corruptions where you may need to fail over. And then of course, there's Mother Nature disasters like we were talking about before. There's the data center floods or all the power goes out or things like that. So the key thing is you want to be comfortable using your standby system, right? So I'll give you an interesting story. Just yesterday, I heard my neighbor right over here trying to start his snowblower, and his snowblower would not start. And I kept hearing him, the engine, it wouldn't turn over. And he was trying to get it started because he knew that we were going to get a lot of snow today, and it didn't start. And I saw the service truck come yesterday, and now we have snow, and he doesn't have a snowblower. So that's kind of what the level of comfort. So what should have happened? He should have probably tried his snowblower maybe on a regular basis and just make sure that it worked. So that's the type of thinking we want to have with our standbys. We don't want to hope that a standby switchover or failover works. We want to know that it's going to work, and we want to test it and make sure that it's going to work, right? So make sure that you have that mindset. We've been working really hard over the years on redo apply rates. You can see the redo apply rates are very high on Exadata, right? And they've gotten even higher now. In 12CR2, we have something called Mira, or multi-instance redo apply, and that allows us to leverage rack systems for the redo apply. That was something that we worked on for a long time, and it's in now. So, excuse me. The other thing, just a couple quick notes about failovers and switchovers. I don't have a slide on this, but best case scenarios, and we test all this stuff internally, we can fail over in as fast as 30 seconds, okay? We can switch over in about the same amount of time. Those are best case numbers, all right? So your mileage may vary on some of this stuff. There's a number of factors. The number of PDBs is a factor. For example, if you're using multi-tenant today, the detection time is a factor. We have something called fast start failover that has a built-in detection mechanism that'll help you fail over. So detecting a problem, and knowing that it's a problem worthy of failing over takes time. But I just want to get you thinking in terms of how quick some of this stuff can be done, you know, if you have to fail over. So. This video shows a database node update. All right, so we're going to be using our patch manager tool to do a database node update and have minimal to no impact to the system. All right, what we have here is we have a software update window over here. We have a window showing how many sessions are connected to each instance in the upper right-hand corner. And in the lower right-hand corner, we have a transactions per second. It's a workload transaction monitor. So let's just walk through this thing a little bit. It's a 1-minute video, but I'm going to pause it a couple times and show you some stuff. You can see we have very even session distribution here, and we start our patch manager session over here on the left. So let me pause it for a minute. See what's starting to happen. This is where the feature that I wanted to describe to you is we have something called RHP helper, or Rapid Home Provisioning helper. And what it allows us to do is to drain work off of a node before it's patched. This is a very important concept. You need to be able to drain the work gracefully, because it does two things. It allows your application to not have to worry about processing errors when sessions are all killed, and it allows the instance recovery to be minimized or eliminated completely when the node goes down. So basically, it allows us to gracefully close an instance and not abort an instance, because an aborted instance needs to be recovered, which causes a brownout or a blackout. Okay, so let's keep going and watch this. Watch this run. You can see all the work is now on the red. So we've moved everything over to the second node, right? And what we're going to see come in here, I'll pause it there for a second. The only impact you see to the system is the rack reconfiguration. When we shut that first instance down completely, some of the mastership, so you know we have global NQ services and global cache services, the mastering of all this stuff, it's the way that real application clusters works. If you had some locks that were mastered on that node and they need to be moved over to the other node, there's a very small brownout associated with that. So that's what you see there. So let's keep going. Now we're going to see the node like completely reboot. There's going to be a window that comes in. See how the system is going down for reboot now, because we're doing a full database node update. So we're taking in a new Exadata image here. So now we're done. What this is going to show is adding cells to an existing system. All right, so we have kind of the same type of window setup. I'm going to pause it for a second. Now, there is very likely something in here you have never seen before. Okay, if you look at the upper window, we have a utility called OEDACLI. So you probably know about OEDA because it's our deployment tool. But OEDACLI is a client utility that we have now that does things like create, it can drop and add databases. It can drop and add cells. It does all sorts of different lifecycle operations. It can upgrade GI, things like that. So it's kind of a post-deployment lifecycle operations tool. And one of the things it can do is add cells. So you can see we have a control script up there to add the cell, and it's going to automate all of the steps required to add a cell. And it does it through like a clone feature. It basically looks at an existing cell, and then it creates all the new configuration for the new cell. So on the bottom, we're seeing whether or not the system is impacted by this activity. So you can see things are running there, and it's basically telling you, you know, here's the XML file that we passed to this OEDACLI, and we're just going to add it in. And there's kind of a lot involved in adding a new cell, right? So you got to do things like, I'll pause it for a second. You got to add your new grid disk, your new cell disk. You got to make sure flash cache is in the right configuration. You have a cell IP.org. You have a cell init.org. All these things are fully automated by this tool, and you can just run it like this in the background. So we're going to let it finish. And okay, so what it's showing now is it's showing the addition of the cell in at the ASM level. So obviously, once everything is done on the cell, we're going to add the cell in at the ASM level. And we use our best practice default power of 4. ASM power is the number of outstanding IOs that an ASM rebalance will issue, okay? The higher the number, the faster the rebalance. The higher the number, the more potential that it might impact your system. We've done a lot of testing, and on a bare metal system, the power should be 4. If you have an OVM system with many clusters, you should try to make the total number for power across all of them to be 4. Okay, this is all in our best practices and in Exachk and everything. So that's going to run this cell ad, and you can see that the system, oh yeah, there's right there, the system is not impacted by this cell addition. Now, how is that? One of the things that we do when we're doing a rebalance is we make sure that data that was cached on the source cell, if we're moving it to the new cell, we make sure that we put it in the flash cache, okay? That's why the system isn't impacted. The performance of the system is very important in this operation, and we make sure that anything that was cached on the existing cells will be cached on the new cells, all right? So we go through that, and that's pretty much it, and we have a new cell. So I'm guessing that you probably didn't know about OEDACLI, because when I speak with customers, most of them haven't really heard about it. I don't think we've gotten the word out as much, so hopefully that's interesting for you. So when we're doing a project like this, we look at the nitty-gritty details. One of the nitty-gritty details, because you all are techies, I think, that you'll like, is we have something called an Exadata AWR report. And in that Exadata AWR report, we have something called single block read histograms. What this does, and this is really nifty, is it breaks out all the single block IOs that are happening into these buckets. And we know this is an OLTP system, so we know that it's a lot of single block IOs. And for our baseline, when we were doing this project, we looked at our cell single block read histogram, and we noticed the following. You see, right here is where the lion's share of them are. Most of the IOs are less than 256 microseconds. 90 some odd % of them are less than 512 microseconds. So that was our baseline. And then we gathered the data during the cell addition, and we basically saw the exact same thing, if you look here. So the reason that the service level wasn't impacted on the previous video that I was just showing you is because the IOs are hitting the flash because we proactively cache that data on the new cell, you see? And this is proof of it. And I want to give a shout out to this Exadata AWR report. If you don't know what this is and you have an Exadata system, you definitely want to check it out. It's a very useful tool, and I would say it's probably the very first thing you should look at with any performance problem. It does all sorts of things. Actually, I have one example on the next slide from a real customer that shows one of the cool things it does. It will detect outliers on your system. So in this case, it color codes everything. Anything that's in burgundy red is usually really bad. So you see in this particular case, we had a cell that was generating way too much physical hard disk IO. And this was slowing this customer's system. This was a big customer, by the way, and it was slowing their system down significantly. And you can see 3 of the disks were just completely saturated. What had happened is this cell did not have write-back flash cache on. And so many IOs were not hitting the flash and hitting these disks. So here's another internal detail for you. So the way that we cache data on the cells is, if you look at a typical Exadata cell, it'll have 12 disks, and it'll have, for example, 4 flash cards, right? So each flash card caches data from 3 hard disks. So when you see a case like this, where 3 hard disks are all burgundy, there's a good chance that like something was wrong with potentially with the flash card associated with that, with those 3 disks, right? So that's just the way that the flash mapping is set up. So all we had to do in this case with this customer is turn on write-back flash cache, and the problem was solved. So where are we and where are we going? So probably you got it just for this, but in the old days, and by the way, the red is Oracle and the blue is the customers, right? So in the old days, on the MAA team, we would write white papers, and as I mentioned in the beginning, we would deliver it, and the customer would have to do most of the work, right? And then like 10 years ago, we came out with Exadata, and we were able to bake more things into the Exadata, especially configuration best practices. Not so much operational, because the customer did all those types of things. And then, we came out with a cloud platform, something like Exacc, where Oracle is able to implement more operational best practices because we own things like the DOM 0 and the cells and the switches and all that. So, and then ultimately where Oracle and the MAA and Exadata, everybody is aligning is around the autonomous platform. So one of the the prime directions for us right now is working very closely with autonomous database and making sure that all the MAA best practices and configuration, operational, everything is built right into the product.
Great. This has been very interesting. Let's now move on to the questions. A lot of clients question the HA over just one rack of Exadata.
So there's a couple things there. First of all, I don't think the rack in all my time has ever been like, we just don't see rack failures in Exadata. All the components are redundant. We have separate PDUs, we have separate PSUs. I mean, we've done tests where we've turned a whole PDU off, right? And the system just continues to work, for example. So I would question the assertion that says a rack is a single point of failure in there. So now, also, if you have multiple racks, you don't have to just use a standby in that case. You can multi-rack systems and have them be part of one cluster. Now, I am always a proponent of a standby database, like ideally a local standby database for corruption protection, right? And obviously, a remote standby database for disaster protection. So, but we just don't see a rack be a single point of failure. If you've seen a rack be a single point of failure, or customers have seen that, I would love to get details on that because we just don't see it.
What are the toughest problems that you solve in high availability? What are the ones that are, I think you alluded to some of them in your examples, but maybe you can give us an overall sense.
Yeah, the toughest, the toughest problems are, I call them sick components. Like you saw in some of my slides, I have sick disks or something like that. I think that's kind of caught on because I see other people using it. But the hardest thing, like we usually have the correct architecture, but when a component is sputtering, any component, whether it be hardware or software, if it's sputtering, what I mean is it's not doing what it's doing something, but not what it's supposed to do. It's not meeting its own service level. That can have a compounding effect on the system.
Right. So I like that you describe it like this because that's very intuitive. When I was an academic, we talked about that by defining it out of the discussion. We would call components fail-stop components. We would say that we only study systems where the component is either perfectly well or completely dead.
Yeah.
Because we knew that was very hard.
Yeah, exactly.
Yes.
Yeah. Unfortunately, we don't control components getting sick on Exadata production systems, so we have to deal with it.
Obviously, that's why academics. Yeah. Okay. So you did give some example, right? So basically, the idea is that the component is misbehaving, sending data at the wrong rates, or sending the wrong data, or not responding to controls consistently.
Yeah, those are tough because you need to know when you can take it out. Like one of the examples is the disk confinement I mentioned. If we detect the disk is not performing well, we'll actually take it offline and run a bunch of diagnostics on it to see if this disk is okay. We'll run something called ORION, which is an IO generator, and say, are the service times in this okay? We run reads, we run writes. We try and figure out if it's okay. If it looks okay, we'll put it back online, right? If it doesn't look okay, we'll drop it. But those are the toughest types of problems because you need to really put in a lot of extra code to deal with those things.
These are things that are the hardest things to communicate, which I consider in the category, what I call the why category of how we do things, right?
Yeah, yeah.
How do you find out that MAA works?
It's definitely true that bad news travels faster than good news. Good news doesn't travel at all sometimes. So, and most of my days are spent trying to make our solution better, which always means you're looking at things that, could be even better than what they are. And I get involved in all sorts of different things. It's just the way the world works. But I do hear a lot of success stories. I mean, I was at Oracle World this past year, and there was one customer I talked to, and they've been running on Exadata for 5 years, and their service level never was compromised the whole time. And we had the 5.9s thing, the 5.9 stamp from IDC a few years ago. If you run Exadata in an MAA gold configuration, which everybody knows what that is now because I explained it at the beginning. IDC external firm, stamped us with a 5.9s compliant. So those types of things are good because you hear some good news as opposed to always dealing with okay, how do we do this better?
That concludes our February 2019 office hour. Thank you, Michael. Hasta la próxima.